Okay, so we're going to talk about uh, discrete structures still, but in this case, we're going to take a look at a function, right? Now, in general, right, the same definition we use for a function in algebra serves us here in discrete math. So a function is a rule that assigns each input exactly one output. Okay, now the main difference here is that we are dealing with discrete sets. So whereas before we would imagine a function being defined across all real numbers, for example, we don't really think about it in that way here, right? We have some sets, not necessarily finite, but definitely what we call countable, right? And that can be written in some kind of order, right? Like our integers. Okay, so here we have a function that assigns a role for an element in set x onto some set y, right? Can more abstractly we can think of, right, this being our set x, this being our set y, right? And there's a rule, right? All elements here have exactly one output in y. All right, and not necessarily that the set covers all of y, right? But all the outputs will be found in y, right? The set x, something called the domain. All of the set y called the codomain, right? And if we look at one specific value of x that goes into the output, right? One instance of this is what's called an image, right? And apart from the codomain, you probably heard of the range. The range are the actual outputs. Or the set of all images, which can vary, right? So here, a brief example here. So let's say we had here -3, and our rule was just the negative x. Right, so you could say f of 1 is -1, f of 2, -2, f of 3, -3. All right, and we can describe this function also as a set of ordered pairs. All right, and these are ordered, right? The first element is the domain, the second element is its image. Okay. Hey, come on. Ah. Okay, excuse me. Okay, so we have functions. These are functions, again, a lot of similarities, very same vocab that we use in algebra. It's just in the set that we are defining them over, right? They are not discrete sets as opposed to like f of x equals to x squared, and we think of that as the parabola, right? Now, much more loosely here, uh, besides functions, we have this idea of relations, right? And relations is very broadly just a set of ordered pairs of elements from A. Right, now here we don't necessarily have we don't have the F notation, right? Because it's not required for each element to have exactly one output, right? Sometimes many elements might satisfy the given relation, right? And what I mean by that is maybe we have when x is less than y, right? As an example here, okay? Depending on the sets, there may be several values of x that can correspond to a y, or several values of y that can correspond to an x, right? So we just have a looser definition here, right? Usually binary between x and y, but not necessarily binary, we can think of like maybe triangular numbers, right? To be the relationship between x, y, z, such that x squared plus y squared equals to z squared, right? And this is our relation that we have uh, here. So that can describe uh, three sets across three numbers from a given set. Okay, but usually for the most part, here we'll look at binary relations. Right now, the notation here we'll introduce here is when there is a relation between x and y, we use something like this. Right, it's little tilde r for relation xy. Sometimes the x r y, right, and then sometimes xy element of r. All these notations represent the same thing. In other words, that there is some relation established between x and y. Now, one particular property for a relation we're going to take a look at is something called this idea of transitive, right? So a relation R on a set A is transitive provided for all x, y, z element of A if x, r, y and y, r, z, then x, r, z. Okay, so now we'll get into some proof writing across these discrete structures.